Assalamualaikum and hi everyone. My name is Muhammad bin Muhammad Nazvi from Acad Systems, and today I'll be giving you guys a little short lecture about static and model analysis. So what is, wait, hold up, sorry. So what exactly are we trying to do here? So static and model analysis follows on a specific topic in Inventor called FEA or finite element analysis. So what exactly is finite element analysis? Finite element analysis is basically where you have your product over here, and then from there the program will make small little triangles all around the model so that it can, and then from there it will calculate your stresses and your strains and shear forces and everything. So instead of just calculating this whole thing, it will calculate inside all the small little points inside the nodes inside here, if you can see. So okay, later I will show you guys more. So it connects at the nodes. So why is this important? This is important because let's say this is quite a really simple object. So let's say if you have a complex object that has either multiple holes inside, or maybe you have some, okay, someone's trying to go in. Hello, good evening. So anyway, so let's say if you have a quite a little bit more complex shape, maybe you have circles, you have holes all around here, then it gets difficult to calculate by using formulas. So instead of us trying to calculate it manually on our own, why not we have the computer calculate it for ourselves? So from there, it simulates physical behaviors based on materials, loads, and constraints. So let's go to static analysis, the basics of static analysis. So what's the point of doing static analysis? Static analysis, the main thing we want to achieve here is to find the stress and the strain of the object based on the forces that we specified on which part of the product. So for example, over here, I have a cantilever. So here we will have a support. So since usually cantilevers are fixed onto a wall, and then from here, this is free floating. So because of that, it will experience some sort of force. So the inputs here, what do we have to put in order to get our results is of course the main geometry of the object. Without the shapes, we're not gonna get any results. I think it's pretty obvious. And then of course material properties. Material varies differently between different types of materials. Some materials have a much steeper strength strain graph. Some materials have it a little bit more less. Some have it a lot less steep. And of course, we have some materials like plastic have a different, what they call different behaviors than say metal. So next, of course, we have the loads and the constraints. So later on, I'll show you guys the different types of loads and also the different types of constraints that are available to us in FEA analysis. So what are the outputs? Mainly, this is what we want to see: volumetric stress, displacement, and factor of safety or safety factor. This is usually the most important. As you can see here, this is roughly what it will look like. Okay. So here, usually inside the program itself, it will calculate it based on how the amount of whatever, let's say, your stress that it experiences. The red color is usually the most, while the blue is the least amount of pressure that is experienced. So next we have modal analysis. So modal analysis is quite a little bit different from static analysis because modal analysis is actually a dynamic analysis, meaning it moves through a space. So static analysis is just static, it doesn't move. So that's where strength and your stiffness comes into play. However, when it comes to modal analysis, since the object moves, you can't really just use the same math, the same calculations that you do in static analysis. So because of that, model analysis or specific, or I guess dynamic analysis is a lot more complicated. However, due to limitations in Inventor itself, we're gonna use normal Inventor instead of Inventor, what they call Nastran. We can only really do model analysis inside there. So what's the point of model analysis? What really is model analysis? So model analysis is actually you try to find the natural frequency of the object. So as we all know, every single solids, the particles inside the solids, the atoms are actually shaking. They shake at a specific natural frequency. So the point of model analysis is to find those frequencies and look at the different shapes of the objects depending on the frequencies that it vibrates at. So why do we need to find the natural frequency? It's obviously, I think, is to avoid resonance. So resonance is when, let's say you have a cantilever here and it vibrates at a certain frequency. If we supply a wave, another force in the form of wave towards the cantilever that matches the natural frequency of the cantilever, what will happen is that the forces from the vibration will become resonant. So what happens is that it get amplified, and so because it amplified, it will break is much more easily. So what are the inputs in order to get the results that we have over here? Obviously, it's our geometry and material mainly, and also constraints. It's the same really. So the outputs, unlike static, we're not concerned with bond stresses, displacement, and safety factor. We're much more concerned with the frequencies, how it vibrates at different frequencies. And of course, as a little bonus, we can actually see it animated, how it moves around in space. Okay, so here's a short little comparison. So you guys can just a little, what do you call, checklist. So you guys can just decide on which what do you call which analysis that you want to use. For example, first we have static, and of course we have model over here. So the different goals for static, we're just trying to find the stress and deformation of the object, whereas in model analysis, we're trying to find natural frequencies and mode shape. So another big difference is that in static, we need to have a load applied to the object itself, because without load, we can't really calculate stress, can we? So when it comes to model, we don't need loads because it's just vibrating. That's what we're mainly concerned with. And so what are they used for? Static is just used to check the strength of the part, whereas model is used mainly to check the behavior of the vibrations, the behavior of the products at different vibrations. So we have output, we have stress plot, and we have animated mode shape. This I'll show you guys later. Okay, so that's all for my slides. Let me just show you my Inventor. Okay. Let's see. Can you guys see it? Can you guys see my screen? Okay, there we go. I think you guys can see. So this is, I just drew this just now. So for example, for the first example for study, I'll just do it on a simple cantilever beam. We have an I-beam over here. So once you finish drawing, how do you get into the what do you call analysis environment? So easy. From there, you just click on here, environments. And so as you can see here, we can either go to stress analysis or we can go to Inventor Nastran. Inventor Nastran is basically a more specialized tool set specifically for analysis. But however, for today, I'm just gonna show you guys the basic, simple analysis that we can do inside normal Inventor Professional. So just click on here, stress analysis. So we are now inside the analysis environment. From there, just click on create a study. So from here, you can change the different types of studies that you want to do. You can do static and model over here. And also you can use shape generator. If you guys remember, my last class, I did make a really short, what do you call, short lecture about shape generator as well. Where after we generate a shape, we have to go to we have to do a static analysis again. So either way, let's just create a new study over here, static analysis. And so here are the things that you need. So firstly, usually what happens is you have to, here we have preparation. You prepare your parts in order to in order to make the analysis go faster usually. So usually, let's say you have a really complex shape over here, it's best actually for you to simplify it down first. Let's say maybe you have some fillets that are more cosmetic, you can remove that, and so on and so forth. So either way, firstly, let's assign a material over here. Click assign material. And from here, in order to assign a material, you just click on materials over here. Here you can see what type of material you have. Generic. Usually currently we have just the generic material. So click on there. I'm pretty sure you guys can see this. Yes, you can. So from here, we have our materials library. Just click on whatever material you want to make it out of. I'll just pick steel. Carbon steel, high steel. Let's just make it stainless steel. So click on the material you want and then click here. Add material to document. And from there, make sure it's selected and it's already that material you can see up here. Also, let's say you guys have your own material that is not inside here. You can also just click here. Here we have the edit button, edit material button. And then from there, you guys can change your, let's say the specific material you have is made by a certain manufacturer. You can just click here and here. So there's a new URL to the product itself. And then here we have the physical properties of the materials. So we have thermals. We are not doing thermal studies right now. So the main thing you want to focus here is mechanical. You have your Young's modulus and also the Poisson ratio. This is what will determine the stiffness of your products. And also the density. The density, we're not going to really use it outside of dynamics. And so either way, just click on cancel for now. Make sure stainless steel is selected. Okay, there we go. And then from there, I believe we can go to personal. Yes, we finished assigning material. So from there, we pick our constraints over here. So what constraints do you have over here? So in normal Inventor Professionals, you are limited to just three different types of constraints. In, let's say, if you guys have Inventor Nastran, there's a lot more different types over here. So I believe there's 5 different types of constraints, but right now we only have 3. So we have fixed, we have pin, and we have frictionless. So what's the difference between these 3? So fixed support is when it is fixed at a point, it doesn't move. So because it doesn't move, it transfers your moment and also at the same time your shear force. So for this cantilever, I'm just going to click on fix because it's going to be fixed to a wall over here. Make sure you select the surface that is fixed. You don't want it to be over here. This is the edge. If you click over here, that means only this edge is well fastened into the wall, so it can go like this instead of going strong like that. So let me just cancel it. Let's go to fix. Okay. So what's the difference between fix and pin? So the fix and pin are actually quite similar. However, the difference is, if you see on our tooltip over here, pin, it can rotate. It can rotate through the axis. It can't move, but it can rotate. So what happens is, because it can rotate, I believe it doesn't transfer, it transfers moments, but it doesn't transfer shear force. Or was it the opposite? I'm not sure. So anyway, it's either one of those two. It either doesn't transfer moment or it doesn't transfer shear force. So because this, we can't rotate this part from the wall, so it's gonna be fixed. So what is frictionless support? Frictionless support is, for example, you have a bearing or you have wheels. The wheels or the bearings will bear load when it comes to, for example, your weight. However, there is no friction. We assume there's no friction because the objects can, we assume that it's going to be able to move freely about the surface. So that's when we use frictionless. So from there, we finish with our constraints. Next, we pick our loads. And so over here, we have these different types of loads. There's also more. We have remote force and body. So mainly what I want you guys to focus on here is mainly just force and also pressure. So what's the difference between force and the pressure? So if I click on force here, let's say around here, so you can see there's one arrow. However, if I put pressure, you see, we can't put it on the edge. We have to put it on the surface. So what happens if I put it on the surface? You see there's multiple arrows over here. So the difference between force and pressure is that if you remember what's the formula for pressure, pressure is force over area. So because of that, when you want to pressure only works, for example, if you have a force that is distributed among an area, you have pressure. Usually this is more towards, let's say you have a valve and you want to, after doing some computational fluid dynamics, you want to see how well the valve actually is able to withstand the forces from the flowing water. You can use pressure in kilopascals or whatever. But since we're not going to be dealing with that, I'm just going to use force and click on where it is applied. So over here. So from here, you can select the directions. So if I click on directions, let's see, this should work this way. Nope, sorry. So you have to pay attention to the arrow. Where is it facing? So let's say from here, you should be able to pick the directions that you want it to face. Let me just, what happens if I click there? Yes. So if I click on this edge, the force will face this edge, will go in the same direction. It is parallel to this edge. However, let's say you don't want to use this edge. Let's say you have a force applied here and there is nothing that you can do in order to, well, normally to make it parallel to. You can also use the vector components. So here you have to pay attention to your, what you call, axis over here. So for example, I want it to go down. So I need to go down with a magnitude of, I believe it's 1000 newtons. Yes, 1000 newtons. So if I want to go down, if I look over here, we are in the y-axis. I need to go down. So I just put negative 1000 over here. So if I click on apply, yep, it faces on the correct direction. So click on cancel. So next, we're done with our pressure. We can now generate our mesh. Okay, welcome. So this is where all the calculations will actually be done through the meshes. As you can see, there's little shapes all around. So let's say you think that this shape, the mesh is not as small as you want it to be. Let's say you want it to be more accurate. So from here, you just click on over here, we have the mesh settings. And from here, you can change the element sizes. For example, I believe it should be 0.01. So what happens if I change the element size? Okay, sorry about that. So what happens if I change the element size? So as you can see over here, this is our tree. Just now we already put our load and our constraints. However, our mesh, now there's a lightning silver symbol over there. What that means is that we now have to update the mesh. We have to update so that it reflects the changes that we wanted that we made to it. So now as you can see, the meshes are a lot smaller now. So what happens now basically, because the meshes are smaller, there is now a lot more calculations that needs to be done. However, because there's a lot more calculations, it is now a lot more accurate. So either way, we finish with our mesh. Now let's simulate. So just click on simulate, just click on run. It's probably gonna take a while, and voila, this is our simulations that we ran. So from here, you can see the von Mises stress. This is how much stress that your part will face given the amount of force that we supply to it. This is 1000 newtons towards downwards. As you can see over here, it color codes these different areas of which over here the stress corresponds to. So over here, as you can see, the stress is the highest at around here, around the contact points at the edges. So it is colored red at 249.6. And the stress is the lowest around the middle over here because there's nothing to be stressed at. Doesn't move against anything. This is the part where it moves the most. And also over here, this is where the force is applied to. So it'll experience some stress over here too. So let's say you want to see in detail the stress that is experiencing at a specific point. You can click on probe over here. So you click on probe, and then you click on the point that you want to see. For example, here we notice there's a little bit of yellowing over here. So I just click there, and as you can see, this is the amount of stress it experiences. So von Mises 200 megapascals. And also you can also animate this. Yeah. If you want to, let's say, look at how the stresses transforms as it moves, you can also click on here, animate. And so this another important thing is displacement. Displacement is how much the object moves. So this part moves the most. So as you can see, this part is in red. The probe also retains from different types of results over here. So you don't have to worry about it. And another important thing is safety factor. As you can see, safety factor is basically the amount of force, a formula of the amount of force, and also how much the object can actually handle without breaking. So as you can see here, some parts are red. So what it means by being red is that this shape is barely able to withstand the amount of force that we supplied to it. So as you can see, this part is red. So the safety factor is 1. This is really bad because usually when it comes to safety factor, we want it to either be at least at the lowest around 1.5 or 2. We don't want it to be 3. So let's say After you're done doing your analysis and let's say you want to change, you can also just click on here, finish analysis, and you can also just adjust your drawings however you want. For example, here, let's say just now, it is not enough. So let's say I made it 20. It is a lot thicker now. So if we go back to stress analysis, from here, we don't have to redo anything. We just have to update. You can just click on update mesh, update context, update the mesh because it is now different, and then just click on simulate. Yes. So as we can see now, if we go back to safety factor, the safety factor is now 1.7, so it is much safer than before. So this design now is overall okay-ish. So that is all under static analysis. Now let's move on to model analysis. So over here, I've made a leaf spring to show you guys the model analysis. So from here, it's just the same thing, just create study, click on model. So number of modes, I want it to be 6. Basically, it now shows that 6 different significant frequencies that this object will vibrate at. So click on OK. So everything is similar to the just now, similar to stress analysis. So firstly, you have to assign the material. Let's say I want it to be, let's make it cast iron, why not? I believe some cars have cast iron leaf springs, I'm not sure. It's okay. And then from there, we don't have to make any preparations because this object is already simple. And next, where is it going to be mounted at? So there's gonna be bolts going through this part, these two parts. So I'm gonna pick fixed. Why do I pick fixed instead of say pin? It's because the bolt doesn't rotate. It's supposed to be solid. It doesn't move. So because of that, I'm just gonna pick fixed. Okay, so click on cancel, that's okay. So load, we don't actually have to put load because, well, this is model analysis. We are not concerned with stresses or anything that requires us to put force. So instead, we can just go straight to mesh view, mesh creation. And then from there, let me just change the mesh to be a little bit smaller. Yeah, I think that's fine. And then from there, we can just click on simulate. Okay, there we go. So over here, if I extend this, we can see how the part behaves at different frequencies. So over here at 144.8 Hertz, it behaves this way, and also displays a very high displacement of 5 at around these two parts. For example, over 6, this is 6,000 Hertz, much higher than the first one. As you can see, it is now a lot high. It now shows a lot more waves inside the part itself. Because if you remember, if you look at the side, Hertz is basically just 1 over time. So this is considered 1 vibration, 1 Hertz. So 1000 Hertz, meaning this will vibrate, it will become like this in just it will vibrate this way 1000 times in just 1 second. Yeah, sorry about that. I had a little brain fart. So because, as you can see, a trend here is that as you go downwards, there's more and more waves. Because essentially, the higher the vibrations, the more waves it will exhibit. This part over here is flat. I'm not sure why. Oh yeah, this is where I believe the natural frequency is 2000. So if you supply just the right amount of frequency, this much, this part maybe will break. So you can also go to animate. You can see it moves too, just like that. So what happens, just now we find that F3 might be the resonant frequency. So what happens if I animate this part? Yes, it just vibrates that way. So if I go here, animate, oops, sorry. Yes, it vibrates this way. There's two different peaks of vibrations. So either way, let's say you finish with your what you call analysis, and now you want it in what you call report form. Sorry, report. Okay, I shouldn't have done that. Okay, it's okay. So from there, you just click on report, and this will generate a report for you. So now it is calculating. Okay, so it finished generating a report. Let me show you guys the report. Where is it? Stress analysis report. So can you guys see it? Yes. Okay. So this is the report. It is in HTML. You can also print it into PDF. So everything is over here. The model. So also the different figures at different frequencies. And also if you scroll down, you should be able to see the maximum. It's okay. So this is a model, so we can't see it. I accidentally closed my static analysis just now, but basically the static analysis should show basically the same thing. However, at the bottom, it will also tell you the maximum amount of stress that your part experiences. So either way, I believe that is all. So before I let you guys go, let me just go to our website real quick, acadsystems.com. Okay, so this is our website, acadsystems.com. So let's say you guys, we do anything Autodesk related. So we sell products and we also offer support for those said products. So for example, let's say you guys are interested in snatching some softwares at a discount, you guys can camp over here, open every now and then and see if there's a sale. I believe there will be a Merdeka sale, but you guys have to just watch out for that. And next, over here, there's also our free online lesson courses and, well, events. So I believe since you guys already joined my session here, you guys should already know what's going on over here. But let's say you didn't know. Let's say you saw some topic that you're interested in. For example, here we have ChatGPT to Auto Lips. You're interested in it, just click on that and then click on RSVP going. So what happens after you click here is that it will send you send you this link to your email around, I believe should be around 30 minutes before the session starts. It sends a reminder basically. And so that is all. Let's say you need some help with your product. Let's say maybe your AutoCAD accidentally crashed or something. You can just go to our help desk and create a new ticket as a guest. So here you can fill up your name and your company's name, and then just click on whatever concern you have. For example, let's say your inventor crash, please help. And then from there, you can set the priority. Let's say you want us to solve it now. You can click on high. And also category, let's say if you want help from me specifically, you can go to KL Technical. However, if let's say you're interested in, well, prices or pricing, or let's say you want Maybe you want discounts, you can also go to sales inquiry. So for example, you go to maybe just pick KL sales. Let's say you want please give discounts. You can also do it this way. So either way, I believe that is all. Thank you guys so much for joining. Be sure to click on the bell and subscribe to our channel, and I'll see you guys next time. Bye bye.